reducing, the best thing would be to reduce the overall energy consumption. The best energy is always the energy not used. And one could think the IT industry should invest more into making the transistors more efficient. We have actually done that the last 50 years. But we're now facing technical problems, or it's even physical barriers that are preventing us from increasing the efficiency of the transistors. And the other problem we are facing is that not the majority of the energy is actually dissipated in the transistors in the chip, but the majority of energy is being dissipated in the wires. And if we're changing or improving the efficiency of the transistors, if all the energy is dissipated in the wires, we don't profit that much. So we're clearly facing problems in increasing the efficiency of the primary process. And what you see here is a summary of the International Technology Roadmap for Semiconductors on topics that are important for transistor efficiency. What you see is the roadmap usually indicates the trend, the technology trend, and shows where most research has to be done. That's the yellow zone. So that means there is no usable solution. Only with a lot of research we can get to a solution. And the red zones show there is no known solution. And you see the problems already start now, that there are, in some aspects, relevant for energy consumption and efficiency. There are no known solutions, so that we cannot have any efficiency increase in the near future coming from the chips themselves. And we need to think how we can keep the pace of the industry as it was in the past, or with this outside political pressure, we would want to even increase the pace. And of course now the raw performance of a computer is not so important anymore, but the efficiency, and there has been quite a considerable increase in one example of high performance computing. The Earth simulator, which was the leading system in 2002, had a efficiency of 3.4 megaflops per watt, and now 6 years later, the leading computer has a efficiency of 445 megaflops per watt, and that's in fact a 27 times increase in performance, and still at a fifth of the overall power consumption. So that was quite a progress. But it's not enough. Still, the trend to more and more power consumption goes up. And we, in fact, should not only count the energy that is going into the boxes, that's this energy, the 2.5 megawatts here, but we should also count the energy that goes into the whole facility. And that would require another metric than we used in the past. And in the past it was the top 500 list, which was the important metric. That will change in the future to the green 500 list, which shows which is the most efficient system among the top 500. And we even propose another list so that the most efficient facility is leading this list. Now I'd like to look a little bit into the past. So what are the historical trends in power density and energy consumption in the last few decades? What you see is that there was a trend in module heat flux going strongly upwards with the former technology that was used for building computers. That was the bipolar technology, which was very fast but not efficient. And that caused an increase in power density per module. So at this point already water cooling was required. Then after this point there was another technology available, which is the current CMOS technology, that has a much higher efficiency. The performance per transistor was not so high at this time when the switch happened, but the overall efficiency was higher. And for this reason, the heat flux, the module heat flux, really dropped down. Now we are on an upward ramp again, and we're even higher than we were at the peak power densities of the bipolar technology, and trend is going strongly upwards. But the problem we have now is there is no technology ready where we can jump to. So we really have to face the problem and try to solve this. One partial solution can come from the process we're developing now, the stacking of chips. So the stacking of chips reduces the wire length in between the functional units. And as I said before, the energy consumption is already dominated by the wire length. So by reducing the wire length, we can reduce the overall amount of energy consumed. But the problem we have this time, when we stack several chips on top of each other, we even increase the heat flux. So on this map, the jump to the next technology, which is 3D packaging, will not result in a jump downwards, but it will be resulting in a jump upwards. So that's why we need to really invest a lot into developing technologies that can handle the high heat fluxes in the future. And that was the motivation for us in the Zurich Research Laboratory to start the project 6 years ago. Another historic trend, the 8088 could be cooled using natural convection without even a heatsink attached. And as we're looking on the trend, Pentium 3, Pentium 4, and Apple G5 here, you see that the volume of the heatsink from the first needed to the current one is at least a factor in 10. We need much more volume for the heatsink. It's much more expensive and also much more complex. This is a water-cooled version, but also the air-cooled versions are difficult or complex because there is not only copper involved, there is heat pipes involved. Here you see them. So it's really very complex, and the trend is actually opposing the trend we see. Boxes become smaller, heat sinks become larger, so that cannot work. So we need to revert that trend. Another historic part was the water-cooled module that was used in one of the IBM machines, 3090. That was on the peak power density of this bipolar trend. And what you see is that there are individual chips assembled on a multi-chip module, and each chip is thermally contacted by this pedestal, and then the whole thing gets water cooled. And this is traditional water cooling using large diameter channels. There were two versions available, air-cooled, but you see this huge volume needed for the air cooler. The liquid cooler was already smaller, but the actual power densities removed by this conduction module is not that impressive, because we can handle now this very same power density easily with air cooler. Now, I said this trend in power density is our motivation to start an increased effort in so-called packaging research. And we think with increased packaging research, and in particular 3D packaging, we can compensate this imminent trend that the efficiency increase and performance increase due to chip scaling. So making transistors smaller and smaller every 3 years is called chip scaling as a process. And the chip scaling was the main driver for Moore's law in the past 50 years almost. And we are now risking that slows down. We try to compensate this by an increased effort in packaging. And when we accelerate this effort, as the other process slows down, we think we can maintain the same pace in the next decade to come. How will the system look like? It's a complex module with passives here in the carrier, and then chips in several layers mounted on top of these interconnection devices.